Okay, so let's talk about the convergence analysis of the ADMM method. So this is the convergence result. Suppose F1 and F2 are convex functions. So let's look at the problem first. So F1 and F2, they are convex functions. And that's the only condition, assumption. Okay. And the gamma is any constant bigger than 2 times the optimal lambda. This lambda is the optimal Lagrange multiplier, but basically gamma is any constant bigger than a certain threshold. And then we have the and then the sequence XT, ZT. Okay, this is running this ADMM algorithm. We have this sequence. We satisfy the following two convergence rates. One is the first one characterizes the sort of like the convergence of the function objective function values. But this F, we will see the definition of F. So this convergence function value decays at the rate about 1 over t. It's a constant divided by t. And this constant involves, for example, the initialization, the distance between the initialization and the optimal point, Z star. And this distance is characterized by so this distance is a special matrix norm. And we will see the definition later. It's different from the L2 norm that we typically use. Now the second result, this one characterizes the convergence, the violation of the equality constraint. And remember in the original problem, we required that AX plus BZ equals to small b. This equality must be satisfied. So this constraint violation, right, it's the L2 norm of the constraint violation, decays also at the rate 1 over t. Okay, so both of these function value and the constraint violation are converging to their errors are converging to zero. And this XT, ZT that we used in this result, they are running average of this generated sequence. It's XK, YK taking a running average. So basically the algorithm, if we run the algorithm, we will generate a sequence XK, ZK. Okay. But this result is about the running average of these generated iterations. And moreover, here for this matrix-based norm, it is defined as follows. So the Z norm to the power of 2, well, this norm depends on a certain matrix C, is defined in terms of this quadratic form. Okay. So this norm is based on a certain positive semi-definite matrix, and it is defined as C transpose C times Z. So the L2 norm is basically C equals to identity matrix. if C equals the identity matrix, C transpose Z is just L2 norm square. Okay. So this is a more general distance metric. And here in this result, we are these norms are based on such a positive semi-definite matrix, rho times B transpose P, for a certain matrix P. So let's look at how these results are proved. Okay. In fact, for the ADMM algorithm, the convergence analysis is a bit complicated. It requires a lot of introducing a lot of notations and big notations. So we will define this because when we run the algorithm, we have 3 updates. We're updating x, z, and the dual variable lambda. Alternatively, therefore, we will, in the convergence analysis, we will need to analyze these 3 parameters at the same time. So here we introduce this omega, which is a concatenation of all these 3 vectors. So omega t is basically xt, zt, lambda t. Okay. And then we will define these 3 different block matrix and block vectors. So G is such a block matrix where all the other blocks are just 0. And we only put A, negative A, B, negative B at in these blocks. This is A transpose, B transpose. And these are just definitions. Vector D is defined by 0, 0, small b, right? Because this is basically calculating the constraint. In the constraint, we have a small b, but for x and z, we don't have any constraint, so we put it 0 on them. And we also define H to be such a block diagonal matrix. Block diagonal matrix. 0, and this is a positive semi-definite matrix, rho times B transpose B. And the last block is rho identity over rho. Again, it's a positive semi-definite matrix. So the entire H is a block diagonal matrix, symmetric, positive semi-definite. And then this is one of the key results. These results characterizes the difference between the function values, the objective function values at an arbitrary point xz and the t plus 1's iteration. Okay. So imagine that you can, so this inequality holds for any xz lambda. So you can set xz to be the minimizer. Then this will give you a bound on the optimality gap. Okay. So on the left-hand side, this is like sort of the difference between these 2 objective function values. And then there we also have this and of course in these 2 terms it only involves x and z, because that is what we have in the objective function value. But again, we have a constraint, right? In the original problem, we have a linear equality constraint. So that is captured by this inner product. Because this matrix G, right, it involves A and B, but A and B are the matrices involved in the constraint. So G times omega is related to that linear constraint that we, it's related to that linear constraint. Therefore, you can say that the left-hand side is about the objective function value, the difference, the objective function value gap, plus something about the violation of the constraint. We will see that more clearly later in the proof. And this lemma says that these terms are lower bounded by the difference between these two distance terms. It's omega minus omega t plus 1, taking the h norm to the power of 2 minus the same norm, but between omega and omega t. So this is like a gap, a difference between two consecutive iterations. And then you can imagine that for the right-hand side, we can do a telescoping, cancel out the intermediate terms. And for the left-hand side, we will have a summation structure. But that essentially will lead us to the final convergence result. So, so what we will do is the following. We will first prove the theorem 10.1. Okay? We will first prove this result, assuming this lemma holds, okay? Assuming this result holds. And then we will come back to the proof of this lemma later. Okay. Now, assuming this is true, what we do is we will set x, z, and omega. So set x, z to be the corresponding optimal optimizer, x star, z star, okay, in lemma 10.2. Basically, right, we can choose x to be x star, z to be z star, and then the omega will become x star, z star, lambda. Okay. Lambda is not specified. So based on lemma 10.2, we specify these two parameters, and then the lemma 10.2 becomes this one. This is exactly that lemma. So this becomes the optimal function value, fx star z star. And then we have this function value gap. This is what we want. We want to calculate the function value gap. And as we said, the right-hand side is a difference between two consecutive iterations. So we sum over k from 0 to t, okay? This one becomes t plus 1 because we have t plus 1 terms. And this is a summation, and the inner product again becomes this summation. Now the right-hand side, canceling out the intermediate terms, we have the first term, initialization term, and the last term. Okay, just do a summation. And now we will define this rounding average variables, omega x, z, lambda. Omega x, z, lambda, they are all. So in the subscript, we put a parenthesis. That means the rounding average of the corresponding variables. Just the definition. Now, what we do is that by convexity, we can. Okay, first of all, this inequality, we can multiply both sides by a -1 so that we can change the order of this inequality. So greater than equal to becomes less than equal to. And this term becomes positive. The optimal term becomes negative. Okay. And then you can see that we also divide it by, we can also divide both sides by t plus 1. Okay. So we only have this term. And these summations will become an average. So we will end up with this. So for example, this term will become 1 over t plus 1 sum over f xk zk. And then subtracting this term. And this inner product term, you can see this, after dividing by t plus 1, this is omega comes here. And this becomes the running average of omega k, which is omega t by definition. And the g omega plus d, that will remain the same. Okay, so the inner product term is and then for this term, this is a running average of all the function values at different xk, zk's. And by convexity, the entire function is convex. So this one is bigger than or equal to the function value evaluated at the running average of these variables. So it's bigger than or equal to xt zt. Because f is a convex function. That's why we get this fxt zt here, just by convexity. And for the right-hand side, since we multiply by -1, so it is the second term minus the first quadratic term. So we can drop that negative quadratic term. So it is further upper bounded by this one. It's a constant divided by t. And this is the final result that we not yet, but this is very close to what we are going to prove. Okay. So we have this result. Okay. Then we need to further look at this inner product term, because what we want is the first two terms. We want to calculate this one. So we need to further understand this inner product term. And we claim that this inner product term equals to this one. Okay. This is just because by these definitions, matrix G and by definition of omega, just plug them into this inner product term and simplify this. Okay. You can check this one, 10.5. Okay. Just simple linear algebra. And you can see that that's how we say, that's why we say this inner product term related to the constraint violation, because it is exactly the inner product term that we see in the Lagrangian multiplier, Lagrangian function. It's the multiplier lambda times the constraint violation. But we just introduce some notations to rewrite it into this form. But it is just the Lagrangian, the term in the Lagrangian function. Okay, now we have this term. Now plug it into the previous equation. Okay, put it back, replace this inner product term by that one. We will have this. Okay, we have this result. And this f, this is the optimal value of f. Okay. Now the right-hand side, this term, again, by definition of omega, it equals to this sum of these two terms. Okay. you can check by definition of omega and by definition of that H norm. So the norm based on H, just plug them into the definitions. You can simplify it to this result. And note that this inequality, up to now, we have what we showed that is that this inequality holds for any lambda, because we start from this llama, and this llama says this one holds for any lambda. Okay. So therefore, here this inequality holds for any lambda. Okay. Therefore, we can take maximum on both sides over this range of lambda. Okay, so we can, so because this inequality holds for any lambda. Okay. Basically, the left-hand side, you can view it as a function of lambda, right? And the right-hand side, you can view it as another function of lambda. And this holds for any lambda, so we can just take maximum. You can take the maximum of over lambda. Here specifically, we take the maximum over this range of lambda. The lambda, the L2 norm of lambda should be less than the gamma. Okay. This one holds pointwise, so we can, so their maximum also holds. And then we can just work out these two maximums separately. For the left-hand side, the only term that involves lambda is that inner product term. So it's a linear function in lambda, and by Cauchy-Schwarz inequality, the maximum value is just the maximum L2 norm of lambda multiplied by the L2 norm of the other side by Cauchy-Schwarz inequality. And for the right-hand side, for this term, again, the only term that involves lambda is this quadratic term. So you can further optimize that very simple quadratic function, and then you will end up with this result. So in this way, we get rid of this lambda. And this proves 10.4a. Let's go check that. So we prove this one. So we actually proved a stronger result because this is a positive term. You can move it to the right hand side and drop it. It doesn't affect this inequality. So essentially, this implies that this optimality gap is bounded by the right hand side. Okay, so that gives 10.48. And then we still have 10.4b. Okay. In general, 10.6 does not establish 10.4b. So what is 10.6? This one. Okay. This result does not imply a bound on this one. Why? Because because this optimatic gap may be negative. And this is because the variables inside, they may not be feasible variables, meaning that they may not satisfy that equality constraint. So it is possible that this value may be small, maybe smaller than the minimum value, because this minimum value is defined to be the minimum value under that constraint, But here, this xt, they may not satisfy that constraint. So this gap, when you run the algorithm, this gap may be negative. But so this part of proof is skipped. But the general idea is that, okay, it may be negative. But fortunately, once we have this condition, this condition assumes that the optimal multiplier lambda has an upper bound. Okay. So under this mild technical condition, one can argue that this gap will not be too negative. So it may be negative, but still it can be controlled in a way. It will not be too negative. So we can develop some bounds on this gap, and then plug in those bounds back into this inequality. Okay, so imagine you can move this term to the right hand side, and then you will have a bound on this constraint violation. And there are some techniques to show that once we have this assumption, this optimatic gap can be bounded by some constants. And that can lead us to this one. So this is the overview of the proof logic. Basically, once we have this key lemma, right, just do a telescoping and you can immediately get the key result. So really it is proving this key lemma is really the most important part for the convergence analysis of ADM. So, okay. So this slice is to prove 10.5. 10.5 is to argue that this inner product is by definition, by plug-in all definitions, is just lambda times this constraint violation. And I will not go into the details, but it's just plug in the definitions and do some linear algebra. Yeah, so eventually you will have these two inner products. Now the first inner product is 0 because this part, by definition, x star z star satisfies that constraint because they are optimized, so they must be feasible. And therefore this is 0. This term is 0. So we only have the second term. Okay, so now let's look at the proof of that key lemma 10.2. This key lemma is really the key to the convergence analysis. Okay, because in this lemma we first introduced these notations, and these notations come from the algorithm. The algorithm iteratively updates x, z, and lambda in a sequential way. So we will have to follow the algorithm and develop this lemma. Now, so starting from the ADMM update rule, these two lines corresponds to the optimality condition of the first two updates. The first update is about x, second update is about z. And remember, so if we go back to the update rule ADMM, yeah, this one, right? These are the first two update rules. They are written as in the form of optimization problems. So the first update rule on X is to solve this minimization problem. On Z is to solve the second minimization problem. Okay. So therefore, we can just we know that the solution would be satisfying the optimality conditions, meaning that the zero belongs to the subdifferential. So you can take subdifferential of this problem, and then zero must belongs to that. Okay, so for example, for the first one, we must have zero belongs to subdifferential of, now considering the subdifferential of these two terms. So zero must belongs to the subdifferential of this entire problem evaluated at xt plus 1. Because xt plus 1 is defined to be the minimizer. And for the second term, it's just the derivative. It's just taking derivative of this quadratic term. So it's just A transpose rho times so that's why we have this structure. So you move this term to the left-hand side. So you have negative rho times A transpose times this big term belongs to subdifferential of F1. Okay? And similarly for the update for Z, you also have this very similar inclusion equation. Okay. So this gives us these are about the optimality conditions for the first two updates. Okay, and then we can build this two inequalities based on the convexity of the objective function. Okay. First of all, these two lines already tells us something about the subdifferential. Okay. So this vector belongs to subdifferential of F1. This vector is part of the subdifferential of F2. Therefore, by convexity, F1x minus F1xt plus 1 plus the subdifferential of F1 at xt plus 1 multiplied by x minus xt plus 1. By convexity, it will be greater than or equal to 0. Okay. So this term is essentially the subdifferential of F1 at xt plus 1. So just plug it in to the definition of convexity. We will have this one. And similarly for this one, this is a subdifferential of F2. So for F2, we also have this by convexity. And you see, by utilizing this convexity, we can start to build some the optimality gap of these functions. We have this optimality gap here. If you sum up these two inequalities, we will have the optimality depth of the entire objective function. So that is the idea. Okay, so let's just put them together. Okay. So so we will add the above two inequalities, sum them up. By summing them up, these four terms will give us fxz minus fxt plus 1, z plus 1. So that is what we have here. Okay. And then for these two inner product terms, again, we will need to sum them up, but you can check that by summing them up, it is equivalent to this big inner product. Okay. Well, here we utilize two things. First of all, we utilize the definition of lambda t plus 1. This is a dual update in the ADM algorithm. Okay, this is by the algorithm. And this is a definition which simply defines lambda tilde t to be such a term, okay, just by definition. So we want to introduce this lambda tilde t so that we can rewrite these two inner products in a more structured form. Okay, so in this big inner product, you can see the left-hand side is all about xz lambda, difference between xz lambda and xt plus 1, z plus 1, and lambda tilde t. So next, we would like to simplify this inner product. Okay, still looks complicated. And first of all, we have this observation. Such a norm such a quadratic term, z minus zt plus 1 times c is a certain matrix, zt times zt minus ct plus 1. This quadratic type of terms can be expanded into 3 quadratic terms based on the C norm. It's just by definition, you can check this inequality. And this is part of the Bregman divergence. Remember, in the Bregman divergence, we have similar structure. This is called 3-point identity. So this is the equality. And then we can also have this. We can also calculate such an inner product. Lambda t plus 1 multiplied by lambda t minus lambda t plus 1. So again, you can just follow these lines, and in the end, you can get this. Everything is equality, okay? So it is exact. In the end, you can get this this result is a difference of four quadratic terms. And then we can claim that the left-hand side is bigger than or equal to these 3. We can drop these positive terms. So we only keep these 3 terms. So we need these 2 intermediate results. Okay, this is one intermediate result. This is another intermediate result. With these 2 intermediate results, we can lower bound this big inner product. We can lower bound it by the difference of these four terms. And in particular, the last two terms, they cancel out with each other. Because this B and C and the definition of C is exactly B transpose B. So these two terms, they can cancel out with each other. So we end up with only the difference of the first two terms. So when you go back to this big inner product, so you see we have this x minus xt plus 1 is multiplied by this one. C minus ct plus 1 multiplied by this one. This will give us this structure. And lambda minus lambda tilde multiplied by this one. Okay. That will lead to this term. Right. So you put all these terms together, and for the rest of the terms, you move it to the right hand side. You can get this result. And this one together with the previous result, putting things together, going back to 10.8. Now this big inner product is now lower bounded by the difference of these two terms. So we end up with this key lemma. And moreover, this term equals to, by replacing omega t plus 1 by an arbitrary, by the same omega. Because of the definition of that G matrix, repeating the prior argument in 10.7, this is 10.7. 10.7 shows that you can make these two the same because of this G is skew symmetric. But you can see that the big picture is pretty simple. You start from the automatic condition of the first two lines of the algorithm. Right? This is some information that we have been utilizing all the way in all the convergence analysis. So based on the automatic condition, we can calculate the self-differential, and based on that, we can utilize the convexity of the objective function to build that function value gap. And all the rest of the steps are just to, when we add these two inequalities together, it looks very complicated, but there is a way to define some notations to simplify all these complex terms. And yeah, these are just labor work. So in the end, we will end up with this very elegant result. You don't see many complicated terms because they are hidden under these notations. Yeah, and this proves that key lemma. This proves that key lemma. So for n in x z lambda, we have this inequality. Okay, so this is everything about the ADMM algorithm for this lecture. Okay, so this lecture talks about the alternating direction method of multipliers. This is really like starting from lecture 7. Starting from lecture 8, when we start to talk about dual method, we talk about the duality and primal dual formulation and several dual methods. And we know that we have mentioned that those dual methods may not be that practical in real applications. But this ADMM method is a very, very popular and it's like golden standard for solving many large-scale optimization problems, especially for network control and distributed optimization. And in the final project, we will utilize the ADMM to solve this low-rank robust PCA problem. To do video surveillance. And this is the exact implementation of the ADMM algorithm on this problem. Very elegant updates, singular value thresholding, soft thresholding. These two is to promote low rankness and the sparsity to the structure, to the solutions. And the last one is the update to the multiplier. In our theory, because L conjugate, sorry, nuclear norm and the L1 norm, they are convex functions. So that theory applies to this problem. So ADMM is guaranteed to converge, and the convergence rate is about 1/t. Okay. So now let's go to the lecture 10. We will just talk about a very different and also I think probably the most important optimization algorithms nowadays, especially in machine learning and data science. It's called stochastic gradient methods. And this type of algorithms is perfect for solving problems with big data. So we start from the algorithm and convergence followed by convergence analysis. And lastly, we talk about some variance issues about this algorithm. So many machine learning problems nowadays can be formulated as this stochastic programming problem. Okay. So what is special about this problem? Now, previously, we were talking about the so-called deterministic optimization problems. So, well, the goal is to minimize a certain function, fx. Fx is given and has explicit form. For example, we have done this least square. Okay, ax minus b. So this function is once you give me the matrix measurement matrix A and these observations B, the problem is fixed, and we just need to solve this problem. But in practice, many of these problems can be written in expectation form. So the objective function value is the expected value of another function, and this function involves some randomness. Right. So this function has an additional variable C. this CSI is basically some random data, some data samples that you collect in your specific application. And these data are usually modeled as random. There are some intrinsic randomness. So we want to minimize the expected loss over this randomness. Okay. So more explicitly, we are going to look at minimize. So fx CSI is what is given a certain sample CSI, given a decision variable x, right? This f function will give us a loss. So the function depends on two things. One is our decision variable x. This is what we want to optimize over. And the other is that it also depends on what kind of data we are playing with, right? Depending on this data sample CSI. But in practice, this CSI could be a random thing. So we want to consider all different possible data. So we want to take the average intuitively. We want to take the expected value of this random function, while the expectation is taken with regard to the taken with regard to this data. So this CSI in practice, we assume that it is following a certain underlying distribution P. Okay, so we want to minimize the expected loss under this data distribution. For example, in face recognition, in this application, this X could be a face recognition model. It could be a neural network, it could be some other machine learning models that you want to learn. Okay. And this CSI is basically an image of a certain human face, right? So basically, so X is your machine learning model. It's a recognition model. And CSI is the image of face. Okay, it's an image of face. And this F is what is basically you apply this model to recognize this image. And this F tells you how the performance is like the loss, the classification loss, or some other loss that you are interested in. Right? And in practice, you have a loss of images, right? There's an underlying distribution of images, talking about different people around the world. And you want to, so what is the goal? The goal is to build, you want to build a model X so that it can, ideally, it can recognize all the images, all the face images. So here, our target is to find an X and a model that can minimize the expected loss over all possible face images. So here we take expectation, meaning that, well, intuitively you want to feed all possible face images into this model and evaluate this average loss, right? And hopefully you want to find a model that can minimize this average loss over all possible faces. So this P is the underlying distribution of ECE, right? We talk about human face. There's always an underlying distribution, um, and it's clearly different from the distribution of cats or dogs. They look very different. So this is just about face recognition, but in fact, any application that involves lots of samples falls into this framework. Where you can talk about face, images of face. You can talk about in language processing. You can talk about sentences or articles that people write. You can also talk about data collected from healthcare. So all the applications that involve data samples, people are essentially doing this stochastic programming. And why do we call it stochastic? Because there's a randomness, right? The underlying data follows a certain distribution. So there are some randomness involved in this data part, and we call this stochastic. So the solution we built or the algorithm we built will need to introduce some randomness to address this type of stochastic structures of the problem. And the key assumption is that this underlying distribution is unknown, or is very hard to evaluate. Okay. Because you don't really know how to model the distribution of human face in general. It's a very abstract thing. So you don't really know this distribution. You may have some intuitive understanding, but you don't know exactly what it looks like. And because we don't know that distribution, we also do not know how to compute the expectation under this distribution. So this is the challenge for this problem. But here we also focus on convex settings. So for every sample to see, this loss function is convex. So therefore, the entire function, the expected loss, or we call it the population loss, is also convex because expectation is basically adding up all these different convex functions, and the convexity is preserved under this operation. Yeah, and there are some other examples, like even the least mean square problem that we talk about. Like this problem, it can be written in terms of a stochastic problem. Because you can check that this one equals to sum of AI transpose X minus BI to the power 2. Okay, assume you have n measurements. AI is the ith row of this matrix A. BI is the ith coordinate. So you see this least mean square problem is sum of these loss functions. So this is f, x, the data is AI and BI. So this AI BI is C. F is the quadratic loss function. So X is the decision variable. So this also fits into the stochastic programming framework. Okay. Now, a very simple solution is the gradient descent. Right. So if f takes this form, I can consider doing gradient descent. And this is gradient descent algorithm. Computing the gradient. Now this f function is the expected loss, right? F takes such expectation form. So we want to take the gradient with regard to this expected loss. And then under some mild conditions, we can swap this gradient and expectation. So it is the expected value of this gradient. So basically, is to evaluate this sample, is to evaluate the gradient for every data sample C, and then we take the expectation over this over C. But we know that these expectations cannot be analytically evaluated because we don't know this distribution P. So this expectation, the challenge is that we don't know how to, there's no way to calculate this expectation exactly. Even if we know evaluating this high dimensional expectation is very expensive because you are integrating a vector over a high dimensional distribution. So it's very complicated. So this motivates us to find some approach to approximate this expectation. And once we approximate it, there are several questions. What is the approximation error? Can we still have some convergence guarantee for this type of algorithms? So that's why the solution we introduced, the stochastic gradient descent. It is a stochastic version of this gradient descent. And the idea is basically using some stochastic approximation to estimate this expected value. We cannot analytically evaluate it, but we can think of some ways to approximate it. So we call this stochastic approximation. So yeah, so today I can briefly highlight the idea. So this is our goal. We want to estimate this expected gradient. we want to estimate this term. Okay, this is essentially the first term, right? The gradient of capital F. But we do not have access to this exact gradient. So we want to find an approximation for the GXT 30. So you can see we are using the same variable xt because we are in the t situation. But instead of computing the expectation over all the ECE, so this expectation is over ECE following the underlying distribution P, but we don't have those information. So instead of considering the entire distribution of ECE, we can sample some ECE T's from that distribution. So again, ECE T is generated from that underlying distribution. For example, you can collect some human face images, right? So when you collect those images, you are basically drawing some samples from the underlying distribution of faces. Right. So we don't really know the underlying distribution, but what we usually have is some specific samples, some realistic samples that we collect from the practice. So so we want to build a certain stochastic estimator, GXT ECE T. Well, ECE T is based on some specific samples that we can collect. And then, of course, here there's a randomness that is about the ECE T. So we, because ECE T is collected from the online distribution. So what we would like that this estimator is unbiased. Basically, the expectation is what we want. The expectation of this stochastic estimator is equals to the gradient of capital F. So at least we want that in expectation, our estimator is unbiased, is exactly what we want. So you see, this is different from setting G to be the capital F. Here we want the expectation to be the gradient of capital F. G itself, every realization of this G can still be very different from capital F, but on average or in expectation, they are equal. And then we have this stochastic gradient descent algorithm, which is basically replacing that unavailable capital gradient of capital F by this stochastic approximation, GXT CT. Because this small g is called a stochastic approximation of the gradient. So we simply call it stochastic gradient. So this algorithm is called stochastic gradient descent. We are using stochastic gradient to do the descent, step. And this is one of the criteria. We want to find a stationary point of this objective function f, but we will talk about this later. So this is the assumption that we adopt for this SGD algorithm. We will use a stochastic gradient whose expectation is the exact gradient. The question is, how do we construct this stochastic gradient in practice? And this can be done in several ways. For example, if we consider this fx, which is the average loss over these samples. So this is basically coming from this least mean square problem. We can write this objective function as a sum of this sample-based loss. But here we take the average. So here we have n samples, I from 1 to n. And 1 over n is taking the average. 1 over n sum over I. This is basically average. Average over the average of this sample loss. Every sample, so we have for every I, we are looking at different sample, AI and yi. You can imagine AI is the image, yi is the label. For example, if we want to do image classification. X is the decision variable that we want to optimize. Now, again, computing the full gradient. In this case, okay, if I want to do gradient descent, then I will need to compute the gradient of this entire summation. And this may involve, depending on how many samples you have. If you have 10,000 or even 100,000 samples, which is not a big sample size, but not for machine learning applications nowadays. Computing the full gradient of this objective function is very will consume a lot of memory and CPU, GPU memories. It is not applicable in many cases. You cannot simply load all the data into a single disk. So we need a way to avoid this computing the full gradient. And a very simple way is to, instead of computing the full gradient, every time I simply randomly draw one sample from this data set, right? And I have in total n data samples, 1, 2, 3, 4, up to n. Every time, every iteration t, I choose an index it uniformly from those from 1 to n. Okay, I just randomly pick one index. Once that index is picked, then I simply compute the gradient with regard to the corresponding loss function. So this is a gradient of the loss associated with that IT sample. Okay. So in this way, first of all, there are two advantages. One, in this way, every time you just need to load one data sample. So the computation now is feasible. We can do it. And second of all, because you are choosing this index IT uniformly as random. So in expectation, if you take expectation of this sample-based gradient, it will equal to the gradient of the capital F. Because IT is a uniform distribution, so by taking expectation, it's essentially as a sample average of all the data samples. So in expectation, this one is exactly what we want. So it satisfies this this condition. In expectation, this stochastic gradient is exact. It's an unbiased estimate of the full gradient. So this is typically how people implement the stochastic gradient descent in practice. Basically, the idea is super simple. You just randomly, if you have a large data set, okay, just randomly pick one, or sometimes people pick a few samples every time, and then compute the gradient with regard to those samples only. But by doing this again and again, so every time you will pick different samples, on average, intuitively, it is like you are still looking at all the samples on average. So SVD is exposing information more efficiently than batch methods. So this batch method is referring to the full gradient descent method, where you need to compute the full gradient every time. Yeah, in practice, data involves lots of redundancy. Using all the data simultaneously in every iteration might be inefficient. In fact, it is impractical for many scenarios. So this SGD is a very efficient solution because it has a very low per iteration cost. Every iteration, we just need to sample one data and run gradient descent. Yeah. And this is the this is comparison between SGD and some deterministic methods. But the intuition is that the x-axis is the number of data samples that we query. You can see SGD is very efficient with regard to the sample complexity. So by querying very little samples, SGD can reach a very low population loss, empirical risk. Yeah. And then next time we will look at the convergence analysis of this SGD algorithm. So here, let's first, the setup is pretty, we will talk about this in more detail next time. But one of the assumptions that we're talking about strongly convex and smooth problems. We have other extensions later on. And this stochastic gradient is an unbiased estimate of the full gradient. And then we require that the second moment of the stochastic gradient is bounded by the gradient. Right? And this can be justified in many ways. Right? So we will talk about this next time. So under this framework, we can have a very strong convergence guarantee for the SGD. Okay. So I think I will stop here today, and we will continue on Thursday. If you have questions about homeworks, talk to me. And for the last two lectures, we have the last homework is homework 9, which is about implementing this stochastic algorithms to solve some of the problems that we have seen in the previous homeworks.
Thank you.
Okay. Thank you, guys. I will see you on Thursday.